The SAMSON TROVIS 3793 Smart Electro-Pneumatic Positioner, configured with its two specialized pneumatic modules, optimizes control performance when using a volume booster on a control valve. Here, the primary output Y1 from one of the pneumatic modules acts directly on the actuator to provide small signal modifications. The secondary output Y2 from the other pneumatic module acts as the control signal to the volume booster, resulting in larger pneumatic volumes being transferred to the actuator for faster movements when larger stroke modifications are needed. Once the deviation from the current and desired position falls below a certain threshold, the TROVIS 3793 Smart Electro-Pneumatic Positioner switches from your secondary output to the primary output. The traditional solution for a volume booster on a control valve would involve tuning the volume booster and positioner to optimize either small signal or large signal controlled performance. If the volume booster and positioner are tuned more for optimal small step responses or small signal, then the results would resemble what is shown on this slide. On small signal changes, the positioner needs little to no assistance from the volume booster. Thus, the volume booster has a large bypass rate. But for large step changes, the full benefit or amplification of control from the volume booster is not engaged enough for optimal control of the valve. The result is a longer than desired time to reach the defined steady state position. Here, we are maintaining stability and sacrificing dynamic response and speed. If we exaggerate this point, then we might have to bypass the volume booster even more to achieve optimal performance on the small step signal. Thus, it would take longer to reach the large set points, and there is now a potential that the desired stroke of the control valve would not occur, as the performance logic of the positioner would time out prior. On the other hand, if we optimized control of the volume booster and positioner based upon the large step response or large signal, we would be reducing the bypass flow. We will have what is shown here in the red lines on this slide. For the larger step response, our configuration provides optimal dynamic response with a quick rise to the set point, no overshoot, and minimal steady state error, as well as maintaining stability with no oscillatory behavior. The small step response of this setup is not as ideal, with overshoot, oscillatory behavior, and a longer than desired time to steady state error. If we look at applications that demand even more assistance from the volume booster, then we might have to bypass the volume booster even less, i.e. 20% rather than the 25% shown here, to achieve optimal performance on the large step signal. The result on the small step signal might become unstable as the oscillatory behavior does not dissipate with time. This instability could maintain a set oscillatory pattern without any hope of control, or worse, form an integration or exponential growth pattern that will cause the valve to destroy itself if unchecked. You could find that the optimal solution for both cases provides a result that was completely unacceptable for the other case. Thus, the optimal solution for the traditional configuration ends up consisting of something that looks like the two non-optimal signals above. Red line from the small step and yellow line from the large step. A TROVIS 3793 with the special pneumatic modular configuration referred to as single acting with two independent channels, allows for the configuration of the volume booster plus positioner to be optimized for both small signal and large signal step changes. As stated prior, the primary output Y1 acts upon the actuator directly and provides small stroke modifications. The secondary output Y2 acts as the control signal to the volume booster, which provides a large volume of air, thus faster movements for larger stroke modifications. In theory, you are tuning the positioner to handle small stroke movements and tuning the volume booster to handle large stroke movements. Since these are independent pneumatics, their interaction and correlation factors are much lower than the traditional solution. Thus, you will notice both green lines provide optimal dynamic response with quick rise to set point, no overshoot, and minimal steady state error.